Bill Nye's latest findings from Voyager 1 reveal something that's honestly keeping NASA scientists awake at night. Here's a mind-bending fact for you. Light from our sun takes over 22 hours to reach Voyager 1's current position. That's just how far this tiny probe has traveled into the unknown. But what it's discovering out there isn't the peaceful emptiness we expected. Instead, Voyager 1 is detecting massive energy storms that shouldn't even exist, plasma waves that could totally obliterate future spacecraft, and magnetic chaos that, well, completely defies our understanding of physics. The question isn't really what's out there anymore. It's whether we're actually prepared for what's waiting in the darkness. The epic journey of Voyager 1. What if I told you that right now as you're watching this video there's a tiny spacecraft hurtling through the darkness of space at 38,000 miles per hour, carrying humanity's message to the stars? Voyager 1 isn't just any ordinary space probe, it's our species' greatest ambassador to the cosmos, and it's been on an incredible journey that started when your parents were probably jamming to disco music back in 1977. This remarkable piece of human engineering has traveled an absolutely mind-boggling 14 billion miles from Earth, making it the most distant human-made object in existence. Think about that for a second. 14 billion miles. That's so far that if you could drive there in a car going highway speeds, it would take you over 17 million years to reach it. What began as a simple mission to snap some photos of Jupiter and Saturn has evolved into something far more extraordinary. Voyager 1 has become our first interstellar explorer, crossing the boundary of our solar system in 2012 and venturing into the mysterious realm between the stars. Every single day, this incredible machine continues to beam back data from the edge of known space, revealing secrets about the universe that we never even knew existed. The fact that this 45-year-old spacecraft is still functioning perfectly in the harshest environment imaginable is nothing short of miraculous, and what it's discovering out there is about to blow your mind completely. The terrifying discovery that changed everything. Scientists are calling it the most unsettling space discovery in decades, and when Bill Nye uses the word terrifying to describe something from space, you know it's serious. After 45 years of silent travel through the cosmos, Voyager 1 has stumbled upon something in the depths of interstellar space that's making even the most seasoned astronomers lose sleep at night. This isn't your typical wow, look at this cool space rock kind of discovery. We're talking about findings that are fundamentally challenging everything we thought we understood about the universe beyond our solar system. The data streaming back from this ancient spacecraft is revealing that interstellar space isn't the peaceful, empty void we always assumed it would be. Instead, Voyager 1 has encountered phenomena so unexpected and potentially dangerous that it's forcing scientists to completely rewrite the textbooks on space exploration. What's particularly chilling is that these discoveries suggest the space between stars might be actively hostile to any form of life or technology that dares to venture into it. The implications are staggering because if these findings hold true, they could mean that humanity's dreams of reaching other star systems might be far more dangerous and complicated than we ever imagined. Bill Nye's concern isn't just academic curiosity, it's a genuine warning about what awaits us in the vast darkness between worlds, and why these revelations from our most distant explorers should make us both amazed and deeply concerned about our cosmic future. Mysterious magnetic field anomalies. Something is seriously wrong with the magnetic fields in deep space, and what Voyager 1 is detecting out there should terrify anyone who dreams of interstellar travel. The spacecraft has encountered magnetic field fluctuations so bizarre and unpredictable that they're completely defying every theoretical model we've built over decades of space research. We're not talking about minor variations here. These are dramatic, violent shifts in magnetic field strength and direction that are happening in patterns that make absolutely no sense according to our current understanding of physics. The magnetic environment that Voyager 1 is navigating through is like a cosmic storm that never ends, with field lines twisting and writhing in ways that suggest interstellar space is far more chaotic and turbulent than we ever dared to consider. What makes this discovery particularly alarming is that these magnetic anomalies could have devastating effects on any future spacecraft attempting to make the journey between stars. Magnetic fields control everything from cosmic radiation flow to the behavior of charged particles, and if we can't predict or understand these field patterns, we can't protect our technology or potential human crews from their effects. The implications are staggering because these findings suggest that the space between stars isn't just empty darkness, it's an active, dynamic environment filled with invisible forces that could tear apart any unprepared vessel. Voyager 1's instruments are essentially screaming back to Earth that interstellar space is nothing like the calm, predictable void we thought we'd find out there. The cosmic ray radiation surge. Your smartphone would be fried within seconds, and a human body would be cooked from the inside out. That's, the reality of what Voyager 1 is experiencing right now in the radiation-soaked nightmare of interstellar space. The spacecraft has detected a terrifying surge in cosmic ray radiation that's bombarding it at levels so intense they're completely rewriting our understanding of what lies beyond our solar system's protective bubble. These aren't just ordinary space particles we're talking about. These are high-energy cosmic bullets traveling at nearly the speed of light, packing enough punch to destroy DNA, fry electronic circuits, and turn any unprotected material into radioactive waste. What's absolutely chilling is that the radiation levels Voyager 1 is measuring are exponentially higher than anything our most pessimistic models predicted, creating a cosmic shooting gallery that would be instantly lethal to any living creature foolish enough to venture into it. The implications for future space exploration are downright terrifying because our current shielding technologies would be about as effective as tissue paper against this interstellar radiation storm. Every second that Voyager 1 spends in this hostile environment, it's being pelted by millions of these cosmic projectiles, and the fact that it's still functioning is nothing short of miraculous. This discovery means that the space between stars isn't just empty and cold. It's actively trying to destroy anything that dares to enter it, turning humanity's dreams of interstellar travel into a potential suicide mission that we're nowhere near prepared to attempt. Implications for future space exploration. Every science fiction movie about interstellar travel just became a horror story, and Voyager 1's discoveries are essentially telling us that our dreams of reaching other stars might be nothing more than elaborate plans for cosmic suicide missions. The combination of unpredictable magnetic field chaos and lethal radiation bombardment that our lone spacecraft is encountering out there paints an absolutely terrifying picture for any future human attempts to leave our solar system. Current spacecraft shielding technology, which we thought was pretty impressive, would be completely useless against the interstellar environment that Voyager 1 is revealing. It would be like trying to stop a machine gun with a paper umbrella. The magnetic field anomalies alone could send any navigation system into complete chaos, while the cosmic ray radiation would slowly cook any crew members from the inside out, turning what should be humanity's greatest adventure into a prolonged death sentence. Even our most advanced robotic missions would face catastrophic challenges in this hostile environment, with electronic systems failing left and right under the relentless assault of high-energy particles. What's particularly disturbing is that these discoveries are forcing engineers and scientists to completely rethink every aspect of interstellar mission design, from propulsion systems to life support to communication arrays. The space between stars isn't just vast and empty, it's actively trying to destroy anything that enters it, which means that reaching another star system might require technological breakthroughs we haven't even begun to develop yet, making interstellar exploration far more dangerous and complex than our wildest nightmares ever suggested. Voyager 1's aging but resilient instruments. How is a 45-year-old piece of technology that's older than the internet still sending back data that's revolutionizing our understanding of the universe? Voyager 1's instruments are performing what can only be described as the most incredible feat of engineering endurance in human history, continuing to function flawlessly in an environment so hostile that it would instantly destroy any modern smartphone or computer. These sensors were designed in the 1970s using technology that's practically ancient by today's standards. We're talking about equipment that has less computing power than a basic calculator, yet it's still detecting and measuring phenomena that our most advanced, Earth-based instruments could never hope to encounter. The spacecraft is operating in conditions that would make Antarctica look like a tropical paradise, enduring temperatures hundreds of degrees below zero, while being constantly bombarded by cosmic radiation that would fry any unprotected electronics in seconds. What makes this even more remarkable is that every piece of data Voyager 1 sends back to Earth takes over 22 hours to reach us, traveling across billions of miles of empty space at the speed of light. The The fact that these decades-old instruments are not only surviving but thriving in the harshest environment imaginable is a testament to human ingenuity and our relentless drive to explore the unknown. Every signal we receive from this ancient explorer represents a triumph of engineering that's allowing us to peer into cosmic mysteries we never even knew existed, proving that sometimes the old ways of doing things are exactly what we need to unlock the universe's deepest secrets. Redefining our understanding of interstellar space. Everything we thought we knew about the space between stars was completely wrong, and Voyager 1's shocking discoveries are forcing scientists to throw decades of research straight into the trash can. Instead of finding the peaceful, empty cosmic highway that textbooks have been describing for generations, our intrepid spacecraft has stumbled into what can only be described as a turbulent ocean of chaos and violence that's rewriting the fundamental laws of astrophysics. The interstellar medium isn't the calm, predictable void we expected, it's a dynamic battlefield where invisible forces clash in ways that make absolutely no sense according to our current understanding of how the universe should work. Scientists are literally going back to the drawing board, questioning basic assumptions about galactic structure, stellar formation, and the very nature of space itself, because Voyager 1's data is revealing phenomena that shouldn't exist according to our models. This discovery is opening up entirely new fields of research that we didn't even know we needed, forcing astronomers to ask questions they never thought to consider before. The implications are staggering, because if we've been this wrong about something as fundamental as interstellar space, what else have we completely misunderstood about our cosmic neighborhood? Every new data packet from Voyager 1 is essentially telling us that the universe is far stranger, more complex and more dangerous than we ever dared to comprehend, turning our confident scientific theories into educated guesses that need complete reconstruction from the ground up. The heliosphere boundary mystery. There's an invisible war happening at the edge of our solar system right now, and Voyager 1 has just sent back battle reports that are making scientists question everything they thought they knew about our cosmic neighborhood's defenses. The boundary between our solar system and interstellar space, known as the heliopause, isn't the simple, clean border we always assumed it would be, but rather a chaotic battleground where our sun's influence clashes violently with the alien forces of deep space. Voyager 1's instruments are detecting bizarre structures and phenomena at this cosmic frontier that suggest our sun's protective bubble extends much further than we ever imagined, while simultaneously revealing that the interstellar medium is actively pushing back against our solar system like an invading army trying to breach our defenses. The heliopause is turning out to be a dynamic, constantly shifting boundary that's more like a cosmic stormfront than the peaceful transition zone scientists expected to find. What's particularly unsettling is that this boundary appears to be fluctuating and changing in real time, with the interstellar medium sometimes advancing deeper into our solar system's territory, and other times retreating under the sun's influence. These discoveries are revealing that our solar system isn't just floating peacefully through space. It's engaged in an ongoing cosmic struggle with the hostile environment beyond, and the outcome of this battle could determine whether our protective heliosphere remains strong enough to shield us from the deadly radiation and chaos that Voyager 1 is encountering in the depths of interstellar space. Bill Nye's call for scientific wonder and concern. When one of the most trusted voices in science education starts using words like terrifying to describe space discoveries, you know we're dealing with something that goes far beyond typical scientific curiosity. Bill Nye isn't just throwing around dramatic language for clicks. He's genuinely concerned about what Voyager 1's findings mean for humanity's future among the stars, while simultaneously celebrating the incredible power of human curiosity that made these discoveries possible in the first place. His perspective on these revelations is particularly compelling because he's spent decades making complex scientific concepts accessible to millions of people, and now he's faced with the challenge of explaining discoveries that are both awe-inspiring and deeply unsettling. Nye emphasizes that while these findings about interstellar space's hostile nature are genuinely frightening for anyone dreaming of Star Trek-style space exploration, they also represent the absolute pinnacle of human scientific achievement and our relentless drive to understand the universe around us. He argues that these terrifying discoveries shouldn't discourage us from exploring space, but rather inspire us to ask bigger questions, develop revolutionary technologies, and approach the cosmos with both profound wonder and healthy respect for its incredible complexity and potential dangers. What makes Nye's perspective so valuable is his ability to balance scientific excitement with practical concern, reminding us that every great discovery in human history has initially seemed impossible or frightening, but ultimately led to breakthroughs that expanded our understanding and capabilities in ways we never thought possible. What the future holds for deep space discovery. Right now, billions of miles away in the cosmic darkness, Voyager 1 is racing toward discoveries that could completely change everything we think we know about the universe, and we might only have a few more years to receive these mind-blowing revelations. As this incredible spacecraft continues its lonely journey into the unknown depths of interstellar space, scientists around the world are holding their breath, eagerly awaiting the next batch of data that could revolutionize our understanding of what lies beyond our solar system's protective boundaries. The clock is ticking because Voyager 1's power supply is gradually weakening, and engineers estimate that the spacecraft will only have enough energy to operate some of its most crucial instruments until around 2025, meaning we're potentially in the final countdown to receive humanity's last direct communications from the edge of known space. What makes this race against time even more exciting is that these groundbreaking findings are already influencing how we design future deep space missions, forcing engineers to develop entirely new technologies that can survive in the harsh, radiation-soaked environment that Voyager 1 has revealed. The spacecraft's terrifying discoveries about magnetic field chaos and cosmic ray bombardment are challenging scientists to create revolutionary shielding systems, navigation technologies, and communication arrays that can function in conditions far more hostile than we ever imagined. Every day that Voyager 1 continues to transmit data brings us closer to unlocking cosmic secrets that could reshape our entire approach to space exploration and our understanding of humanity's place in this vast, dangerous, and utterly fascinating universe. And there you have it. Voyager 1's incredible journey continues to reveal the universe's most mind-bending secrets. The cosmos is far stranger and more dangerous than we ever imagined, but that's exactly what makes space exploration so fascinating. If these cosmic discoveries blew your mind as much as they did mine, make sure to hit that bell icon so you never miss our latest space revelations. Don't forget to subscribe to Simply Science for more incredible discoveries that will change how you see the universe. Drop a comment below and let me know which of these Voyager 1 findings shocked you the most. Until next time, keep exploring the wonders of science. When mysterious objects like 3I Atlas streak through our solar system, how do scientists determine if they're natural space rocks or, something far more extraordinary? The process of distinguishing between cosmic debris and potential alien technology involves rigorous scientific methods, advanced telescopes, and careful analysis of physical properties. From spectral signatures to orbital mechanics, astronomers have developed sophisticated techniques to separate fact from fiction in the search for extraterrestrial intelligence. A rare visitor from deep space. What makes an object suspicious enough to warrant investigation for potential alien origins? When astronomers discovered 3I Atlas in July 2025, they immediately began analyzing its characteristics using established protocols for identifying unusual celestial visitors. The object's extreme velocity of 58 kilometers per second and hyperbolic trajectory initially raised questions about its nature, similar to how Oumuamua sparked scientific debate in 2017. Scientists look for specific markers that distinguish natural objects from potential artificial constructs, including surface composition, structural integrity, and behavioral patterns. Natural interstellar objects typically display predictable properties based on their formation in distant stellar systems, while hypothetical alien technology might exhibit anomalous characteristics that defy conventional physics. The key lies in systematic observation and measurement rather than speculation. Professional astronomers use multiple independent observation methods to verify their findings and eliminate human error or equipment malfunction. Every mysterious space object receives the same rigorous scientific scrutiny, ensuring that extraordinary claims require extraordinary evidence. This methodical approach has successfully identified thousands of natural objects while maintaining vigilance for genuinely anomalous discoveries. The scientific community remains open to finding evidence of alien technology while maintaining strict standards for verification and peer review. The breaking discovery. How do scientists separate genuine discoveries from false alarms when studying mysterious space objects? The confirmation process begins immediately after initial detection, involving multiple independent observations from different telescopes worldwide. When Atlas telescopes first spotted 3I Atlas, teams at observatories across Chile, Hawaii, and South Africa began collecting data to verify its properties and trajectory. Scientists analyze orbital mechanics first, determining whether an object follows natural gravitational physics or exhibits unexplained acceleration patterns that might suggest propulsion systems. Spectroscopic analysis reveals surface composition, helping distinguish between rocky, icy, or metallic materials that provide clues about natural versus artificial origins. The object's rotation rate, brightness variations, and thermal emissions undergo careful scrutiny to identify any anomalies inconsistent with natural formation processes. Professional astronomers coordinate through international networks, sharing data and cross-referencing observations to eliminate observational errors or equipment malfunctions. The International Astronomical Union maintains strict protocols for announcing discoveries, requiring multiple confirmations before official designation. Scientists also consider alternative explanations for unusual properties, exploring whether natural phenomena could account for seemingly anomalous characteristics. This systematic approach ensures that only genuinely unexplained objects receive serious consideration as potential evidence of alien technology, while protecting the scientific community from premature or inaccurate conclusions that could damage public trust in astronomical research. The discovery story. What specific techniques do astronomers use to analyze potentially artificial objects in space? The investigation process relies heavily on photometry, spectroscopy, and astrometry to build comprehensive profiles of mysterious visitors. David Jewett and Jane Liu, pioneers in studying distant solar system objects, established many protocols now used for interstellar object analysis. Scientists measure brightness variations over time, looking for rotation patterns that might indicate artificial symmetries or unusual structural properties inconsistent with natural formation. Spectral analysis reveals elemental composition by examining how objects absorb and reflect different wavelengths of light, providing chemical fingerprints that distinguish manufactured materials from natural rock, ice, or metal. Thermal imaging detects heat signatures that might indicate internal power sources, active machinery, or artificial temperature regulation systems. Radio telescopes scan for electromagnetic emissions that could signal communication systems, navigation equipment, or other technological signatures. High-resolution imaging attempts to resolve surface features, searching for geometric patterns, artificial structures, or manufacturing marks that would distinguish technology from natural geological processes. Scientists also monitor for trajectory changes that might indicate course corrections, propulsion systems, or intelligent navigation, rather than purely gravitational motion. The Very Large Array and other radio telescope networks continuously monitor for signals from objects of interest. Modern computational power allows rapid analysis of vast datasets, enabling scientists to process observations from multiple wavelengths simultaneously and identify subtle anomalies that might escape individual telescope observations. A stranger in our midst. So, how do natural objects behave differently from potential alien artifacts when observed through powerful telescopes? Well, natural interstellar objects typically show predictable characteristics, based on their formation environments and the effects of cosmic ray exposure during their really long journeys through space. Asteroid composition usually follows known patterns, rocky, metallic, or icy materials that are consistent with planetary formation processes around distant stars. Scientists expect natural objects to display signs of space weathering, like surface darkening from cosmic ray bombardment and micrometeorite impacts that build up over millions of years. Their rotation rates generally fall within ranges determined by gravitational interactions during ejection from their parent star systems, and these are typically measured in hours, not artificially precise periods. When it comes to comets, natural outgassing produces predictable chemical signatures as volatile materials sublimate while approaching the sun, creating those characteristic coma and tail formations. The structural integrity of these objects follows physical laws, how different materials respond to gravitational stresses, temperature swings, and rotational forces during interstellar travel. Scientists use computer models to predict how various natural materials would appear after extended exposure to cosmic radiation and extreme temperatures in interstellar space. On the other hand, artificial objects might show unusual geometric shapes, precise rotational periods, unexpected material compositions, or surface features that just don't line up with natural formation processes. The Spitzer Space Telescope and other infrared instruments can detect thermal anomalies, which might hint at internal power sources or artificial heating systems. And with advanced imaging techniques, researchers examine surface textures, searching for manufacturing marks, geometric patterns, or structural elements that would suggest intelligent design rather than natural geological or impact processes. The predecessors. What lessons did scientists learn from previous mysterious objects that shaped current investigation protocols? The 2017 discovery of Oumuamua really changed the game for astronomers, establishing comprehensive analysis frameworks that are still in use today. Robert Warwick at the University of Hawaii was the first to detect Oumuamua, which showed unusual acceleration patterns that initially puzzled scientists, until natural explanations involving outgassing were confirmed. The controversy over Oumuamua's elongated shape and slight acceleration taught researchers the importance of gathering multiple types of observational data before jumping to conclusions. Avi Loeb from Harvard University suggested considering artificial origins for Oumuamua, which sparked important discussions about scientific methodology and the burden of proof needed for extraordinary claims. Then there was 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, which provided a more conventional example of an interstellar comet with clearly natural characteristics. These experiences established standard protocols for studying interstellar objects, like immediate spectroscopic analysis, trajectory monitoring, and international coordination for follow-up observations. Scientists learned to consider both natural and artificial explanations at the same time, while maintaining rigorous standards for evaluating evidence. The experiences with these objects also highlighted the need for rapid response capabilities, since interstellar visitors are only observable for limited time periods before they leave the solar system. Nowadays, modern protocols include automated alert systems that notify astronomers worldwide within just a few hours of discovery, enabling coordinated international observation campaigns to maximize data collection from these rare cosmic visitors. The cosmic journey. How do orbital mechanics help scientists distinguish between natural objects and potential alien spacecraft? Well, natural interstellar objects follow predictable trajectories determined by gravitational interactions with the Sun and planets, while artificial objects might show unexplained course corrections or propulsion signatures. Gravitational physics gives us precise mathematical frameworks for calculating expected paths, allowing scientists to spot any deviations that could indicate active navigation systems. For example, the trajectory of 3I/Atlas follows a hyperbolic orbit with an eccentricity of 6.14, which is totally consistent with natural ejection from a distant star system millions of years ago. Scientists use sophisticated computer simulations to trace backward trajectories, trying to identify possible origin star systems and validate natural formation scenarios. Of course, unexpected acceleration or deceleration patterns might indicate propulsion systems, though natural phenomena like outgassing can also cause trajectory changes in comets and asteroids. JPL's navigation teams keep a close watch on object trajectories using radar and optical observations, measuring positions with extraordinary precision to catch even the subtlest motion anomalies. Artificial objects could show perfect geometric flight paths, precise timing in trajectory changes, or acceleration patterns that just don't fit with known natural forces like solar radiation pressure or gravitational slingshot effects. The Deep Space Network offers radar tracking capabilities that can pick up tiny changes in velocity or trajectory that optical telescopes might miss. Scientists also analyze how objects respond to solar radiation pressure, gravitational perturbations from planets, and other natural forces, just to make sure their motion follows purely physical laws, or to see if it hints at intelligent control systems managing their flight paths through the solar system. A scientific goldmine. What advanced technologies enable scientists to determine if mysterious objects are natural or artificial? Well, modern astronomical instruments provide, honestly, unprecedented capabilities for analyzing the physical properties and behavior of potential alien artifacts versus natural space debris. Spectroscopic analysis, using instruments like those on the James Webb Space Telescope, can identify specific chemical compositions, revealing whether objects contain materials consistent with natural formation or, unusual artificial alloys. High-resolution imaging from ground-based adaptive optic systems and space telescopes can resolve surface features as small as tens of meters, searching for geometric patterns, manufacturing marks, or structural elements that would indicate intelligent design. Radio astronomy facilities like the Very Large Array continuously monitor for electromagnetic emissions that might indicate communication systems, navigation equipment, or other technological signatures from mysterious objects. Infrared observations detect thermal signatures that could reveal internal power sources, artificial heating systems, or temperature regulation inconsistent with passive solar heating of natural materials. Advanced computer modeling allows scientists to simulate how various materials and structures would behave under different conditions, comparing observations with theoretical predictions for natural versus artificial objects. Gravitational wave detectors provide additional monitoring capabilities for massive objects that might employ, say, exotic propulsion systems. Machine learning algorithms process vast amounts of observational data, identifying subtle patterns and anomalies that might escape human analysis. And finally, international coordination through networks like the International Astronomical Union ensures that multiple independent teams analyze the same objects, reducing the risk of observational errors or biased interpretations that could lead to false conclusions about potential alien technology. Unanswered questions. What specific characteristics would definitively identify an object as alien technology rather than natural space debris? Scientists have established clear criteria for distinguishing artificial constructs from natural celestial objects, though, some borderline cases continue to challenge conventional analysis methods. Geometric precision in shape, surface features, or rotational periods would strongly suggest intelligent design, since natural processes rarely produce perfectly symmetrical or mathematically precise structures. Unusual material compositions containing pure metals, artificial alloys, or isotopic ratios inconsistent with stellar nucleosynthesis would indicate manufacturing rather than natural formation processes. Active electromagnetic emissions, especially coherent radio signals or structured data transmissions, would provide compelling evidence of technological origin and possibly intelligence. Propulsion signatures including unexplained acceleration, trajectory corrections, or energy emissions inconsistent with known natural forces would suggest artificial control systems. Surface features showing clear geometric patterns, construction joints, or manufacturing marks visible through high-resolution imaging would distinguish technology from natural geological processes. Internal structure revealed through radar or gravitational analysis might show artificial compartments, machinery, or organized systems rather than homogeneous natural composition. Thermal anomalies indicating internal power sources, temperature regulation, or waste heat disposal would suggest active technological systems rather than passive solar heating. Response to external stimuli, such as changes in behavior when approached by spacecraft or exposed to radio signals, might indicate artificial intelligence or automated systems. The SETI Institute maintains protocols for evaluating potential techno-signatures, requiring multiple independent confirmations before announcing discoveries of artificial objects. Scientists continue refining detection methods and analysis techniques to ensure they can recognize genuine alien technology while, avoiding false positives from natural phenomena. The alien question. How do scientists balance open-minded investigation with rigorous skepticism when evaluating potential alien artifacts? The scientific method requires maintaining both receptivity to extraordinary discoveries and strict evidential standards that prevent premature conclusions about alien technology. Avi Loeb, chair of Harvard's astronomy department, advocates for seriously considering artificial origins when natural explanations prove inadequate, while emphasizing the need for extraordinary evidence to support extraordinary claims. Carl Sagan's famous principle that extraordinary claims require extraordinary evidence guides most astronomical investigations, ensuring that potential alien discoveries undergo the most rigorous peer review and verification processes. Scientists recognize that discovering genuine alien technology would represent one of humanity's most significant achievements, requiring absolute certainty to avoid false announcements that could damage scientific credibility. The SETI Institute has developed comprehensive protocols for evaluating potential techno-signatures, including multiple independent verification requirements and international coordination before making public announcements. Natural explanations must be thoroughly explored and eliminated before considering artificial origins, as the history of astronomy shows that apparently anomalous objects often have conventional explanations discovered through continued observation. Peer review processes ensure that multiple independent scientists analyze the same data and observations, reducing the risk of individual bias or analytical errors that might lead to incorrect conclusions. The scientific community maintains healthy skepticism while remaining genuinely open to discovering evidence of alien technology, balancing the need for rigorous investigation with the recognition that such discoveries would profoundly impact human understanding of our place in the universe and the prevalence of intelligent life throughout the galaxy. Dawn of a new era. What does the future hold for detecting and analyzing potentially artificial objects in our solar system? Technological advances in astronomy continue revolutionizing our ability to identify, track, and study mysterious visitors that might represent alien technology rather than natural space debris. Next-generation telescopes like the Vera Rubin Observatory will survey the entire visible sky nightly, dramatically increasing discovery rates for interstellar objects and providing rapid alerts for international follow-up observations. Advanced artificial intelligence systems will analyze observational data in real time, identifying subtle anomalies and patterns that might escape human attention, while flagging objects requiring immediate investigation. Space-based observation platforms will provide continuous monitoring capabilities without atmospheric interference, enabling detailed spectroscopic and thermal analysis of potentially artificial objects throughout their solar system passages. Improved international coordination through organizations like the International Astronomical Union ensures rapid information sharing and coordinated observation campaigns that maximize data collection from rare interstellar visitors. Radar astronomy facilities continue expanding their capabilities for detailed trajectory tracking and surface mapping, providing unprecedented precision in detecting artificial structures or unexpected motion patterns. Future space missions might include dedicated interceptor spacecraft designed to rendezvous with mysterious objects for close-range analysis, collecting samples and detailed measurements impossible from ground-based observations. The Breakthrough Listen project and similar initiatives continue expanding radio monitoring capabilities, searching for electromagnetic signatures that might indicate technological origins. Enhanced computer modeling and simulation capabilities will enable more sophisticated analysis of observational data, comparing observations with theoretical predictions for both natural and artificial objects to distinguish between conventional explanations and genuinely anomalous discoveries requiring extraordinary investigation. The search for alien technology requires balancing scientific rigor with open-minded investigation, ensuring we don't miss genuine discoveries while avoiding false alarms. As our detection capabilities advance, astronomers remain vigilant for objects that might represent humanity's first contact with extraterrestrial intelligence. Every mysterious visitor gets the same careful analysis, protecting both scientific credibility and our readiness for extraordinary discoveries. Keep exploring the cosmos with Simply Science, like, share, and subscribe for more fascinating insights into our universe's greatest mysteries. Have you ever imagined a spacecraft so far from home that sunlight takes over 20 hours to reach it? Voyager 1, launched way back in 1977, crossed into interstellar space in 2012, becoming the first human-made object to venture beyond our solar bubble. Its instruments, believe it or not, continue to relay whispers from the unknown, probing regions where cosmic rays and magnetic fields dance in this kind of eerie harmony. Here's the punchline. Voyager 1 is still alive, and it's over 14 billion miles away. Did you know its tiny plutonium power source will last until around 2025? Impossible encounter in deep space. A tiny spacecraft more than 14 billion miles from Earth suddenly shook the foundations of modern astrophysics when Voyager 1's instruments recorded an astonishing, milliseconds-long burst of high-energy particles unlike anything seen before in interstellar space. In that instant, every sensor on the probe lit up with an organized waveform, ruling out random cosmic noise and forcing engineers to confirm that this was no mere hardware glitch. At the same moment, Voyager's gyroscopes detected a subtle twist in its orientation, as if an unseen hand had tugged on the craft, and the usual 22-hour round-trip signal delay to Earth shrank by a fraction of a second, hinting at a fleeting distortion in the fabric of spacetime itself. No gamma-ray burst, supernova, or solar storm shows up in astronomical records for that region, leaving experts scrambling through three impossible theories: an extraterrestrial device projecting a focused energy field, a pocket of dark energy that warped electromagnetic propagation, or an interaction with a rare plasma filament weaving through the interstellar medium. Each hypothesis challenges the very core of physics textbooks, demanding we rethink how energy, gravity, and the unseen architecture of the void behave beyond the heliosphere. In the silent expanse beyond our sun's protective bubble, Voyager 1's incredible anomaly reminds us that even the emptiest reaches of space are alive with mysteries, waiting for humanity's farthest-flung explorer to uncover secrets that could rewrite our understanding of the universe. Glitch, just mystery. Voyager 1's ground team stared at the data readouts in sheer disbelief as every single diagnostic test came back pristine. No corrupted memory blocks, no voltage fluctuations, no code errors, nothing to explain the extraordinary energy burst. Systems older than most smartphones performed flawlessly under scrutiny, with checksum verifications confirming every line of onboard software was intact, and temperature sensors reporting nominal levels despite the ferocious particle spike. Even the legendary fault isolation protocol, designed to reroute power and reset malfunctioning modules in mid-flight, lay unused because there simply was nothing to reset. Engineers pored over thousands of telemetry frames, tracing each bit of data back through redundant pathways, and found no evidence of internal interference. If Voyager 1's ancient circuitry didn't generate the anomaly, then whatever happened out in the abyss must have been real, an authentic encounter etched into the probe's history. In that moment, confidence in Voyager's hardware soared alongside excitement for new possibilities, because ruling out a spacecraft glitch meant there was something truly alien at play in interstellar space, taunting our understanding and daring us to chase answers farther than ever before. Voyager 1's celestial Morse code. Voyager 1's data stream suddenly morphed from random static into what looked like a cosmic Morse code, a patterned pulse that left scientists both thrilled and baffled. In a fraction of a second, the probe's particle detectors and magnetometers synchronized to reveal a series of evenly spaced energy peaks, as though an unseen hand was tapping across the void. This wasn't the chaotic hiss of solar wind or the harsh roar of a gamma-ray burst. Each pulse repeated with hypnotic precision, spanning multiple frequencies and lighting up every instrument on board. Mission specialists pored over spectral analyses and discovered that the waveform bore hallmarks of an engineered signal: consistent amplitude, regular intervals, and a frequency sweep that traced a smooth arc rather than flickering unpredictably. Even more astonishing, the pulse sequence carried subtle variations, tiny shifts in timing and strength, that hinted at encoded information rather than a simple periodic disturbance. It was as if Voyager 1 had intercepted a secret broadcast, one crafted by forces beyond human technology. The phenomenon forced researchers to rethink assumptions about interstellar space being a purely random environment. It suggested that pockets of order could exist out there, whether born from exotic plasma structures, alien transmissions, or unknown quantum processes. Deciphering this patterned pulse has become a top priority, with teams applying advanced signal processing algorithms and machine learning models to tease out possible messages or physical explanations. As Voyager 1 continues its lonely voyage, every bite of this mysterious waveform could unlock groundbreaking insights into the hidden rhythms of the cosmos, and remind us that even in the deepest darkness, order sometimes whispers its presence in the language of light and energy. An unseen hand in the abyss. Voyager 1's gyroscope suddenly whispered of a cosmic nudge, an invisible twist that left controllers back on Earth scrambling for explanations. In the span of mere milliseconds, the probe's attitude sensors detected a subtle, inexplicable rotation, a change so slight it couldn't have been caused by solar pressure or micrometeorite impacts, yet unmistakable in the spacecraft's precise telemetry. Engineers pored over torque calculations, eliminating every conceivable onboard cause: fuel slosh, mechanical backlash, thermal flexing, until they were left staring at a phenomenon with no terrestrial analog. It was as though an unseen hand had reached across the void to give the billion-mile-old Voyager a gentle spin, bending the laws of momentum in a region we once believed too empty to exert any force. The unexpected rotation coincided exactly with the instrumented energy spike and patterned pulse, weaving a narrative of interconnected events that defy random chance. This phantom torque raises profound questions. Could Voyager have grazed a dark matter stream whose gravitational tides imparted enough leverage to twist the craft? Might it have skimmed the edge of an interstellar shockwave, where charged particles funnel a directional impetus? Or more tantalizingly, did it encounter an alien probe deploying micro-thrusters in a silent salute to humanity's farthest emissary? As research teams model this ghostly rotation, high-fidelity simulations and laboratory plasma experiments strive to replicate the torque under controlled conditions. Each test brings new clues and fresh mysteries to light. Voyager 1's unexpected pirouette reminds us that even in the supposedly tranquil expanse beyond the heliosphere, forces unseen and unfathomable still hold sway, challenging our understanding of motion, matter, and the mysterious ballet of the cosmos. Accelerated echo. Voyager 1's routine ping suddenly arrived back on Earth faster than light-starved engineers had ever seen, its 22-hour delay shaved by a mind-bending fraction of a second, hinting at a fleeting shortcut through the cosmic fabric. As mission controllers compared timestamps, they realized the signal's return lag dipped by nearly 0.02%, an anomaly far beyond measurement error, and repeated across multiple tracking sessions. This wasn't a glitch in ground station clocks, atomic time calibrations held steady, nor a misalignment in the Deep Space Network antennas which showed perfect pointing accuracy. Instead, the only plausible culprit lay between the stars, a transient wrinkle in space-time itself. Some researchers propose Voyager skimmed the edge of a gravitational lens formed by a dark matter clump, bending its own radio waves and hastening their journey home. Others theorize the probe drifted through a localized warp bubble, an exotic distortion predicted by general relativity but never before observed, compressing the distance light traveled by mere thousands of kilometers. Intriguingly, this temporal quiver aligned with the same instant as the energy spike and phantom torque, weaving a tapestry of interlinked anomalies that defy conventional astrophysics. If confirmed, this phenomenon offers a rare glimpse into how gravity and quantum effects interlace across interstellar scales, potentially unlocking new methods for faster-than-light communication or propulsion. Engineers are now reanalyzing decades of archival data for similar micro-shortcuts, while theoreticians refine models of spacetime foam to account for Voyager's cosmic detour. In the silent expanse beyond Neptune's reach, Voyager 1's accelerated echo reminds us that even the void can surprise, revealing hidden pathways through the universe that beckon humanity to rethink the very nature of distance and time. The Cosmic Detective Story. Voyager 1's ground team frantically cross-referenced every astronomical database on Earth, searching for the cosmic culprit behind the impossible energy burst, only to discover that the universe had gone eerily quiet at the exact moment of the encounter. No gamma-ray bursts lighting up distant galaxies, no supernovae explosions sending shockwaves across light-years, no solar storms from our own sun rippling through interstellar space. Absolutely nothing to explain what had just happened to humanity's most distant explorer. The Deep Space Network's massive radio dishes, which normally detect the faintest whispers of cosmic violence from billions of miles away, registered complete silence in Voyager's sector during those crucial milliseconds. Even more puzzling, the probe's location placed it in what astronomers call a cosmic desert, a region so devoid of stellar activity that it should have been the most predictable, boring stretch of interstellar space imaginable. Teams scoured records from the Hubble Space Telescope, the Chandra X-ray Observatory, and ground-based gamma-ray detectors, finding no trace of the high-energy phenomena that typically produce such dramatic particle spikes. The absence of any conventional explanation forced scientists to confront an uncomfortable truth. Whatever had interacted with Voyager 1 wasn't broadcasting its presence to the rest of the universe. It was as if the cosmos had conspired to create a perfect mystery, leaving behind only the faintest fingerprints on a single spacecraft drifting through the void. In the vast theater of space, where violent stellar deaths and explosive births paint the darkness with radiation, Voyager 1 had encountered something that preferred to remain hidden, making its discovery all the more extraordinary, and, honestly, a little terrifying. Alien architecture. When Voyager 1's detectors lit up with that impossible energy surge, engineers never suspected they might be witnessing the handiwork of an alien civilization experimenting in the dark. Suddenly, This 4-decade-old probe recorded a beam of finely tuned particles, not chaotic like a cosmic blast but precise, like a message or a probe's beacon interrupting interstellar space. Analysis revealed the burst carried hallmarks of intentional design, sharp rise and fall patterns, frequency shifts matching the characteristics of directed energy systems, and a coherence so perfect that natural plasma interactions could never replicate it. As the burst faded, Voyager's orientation sensors registered micro-adjustments in its attitude, as if tiny thrusters had nudged the spacecraft ever so slightly, another signature of a remote station device calibrating its aim. Experts theorize that Voyager may have passed through the scanning field of an extraterrestrial sentinel, its beams designed to map atomic structures across vast distances or to ping interstellar vessels for contact protocols. Alternatively, some propose that an alien research platform deployed a stealth drone using advanced metamaterials to cloak itself until it communicated with passing artifacts like Voyager. In either case, this encounter suggests that we're not the only technologists in our galactic neighborhood. Perhaps somewhere out there, hidden between the stars, lies an extraterrestrial network of sensors and beacons, silently cataloging the interstellar medium and cataloging every human-made emissary that dares to venture beyond its home system. Voyager 1's brush with alien technology isn't just science fiction come to life, it's the first breadcrumb on a trail that could lead us to the architects of the cosmos, challenging humanity to listen more closely to the silent symphony of space. Dark energy pocket. So, a sudden distortion in Voyager 1's data hints that the probe may have drifted into a pocket of dark energy, a region where the mysterious force accelerating the universe's expansion really takes center stage. In this hypothesis, Voyager 1 crossed into an extraordinarily empty patch of space, way emptier than the surrounding interstellar medium, where the repulsive effect of dark energy briefly overwhelmed all other influences. Instead of the usual cosmic rays and plasma interactions, the spacecraft detected these subtle shifts in its electromagnetic signals, frequencies that stretched and compressed as they moved through a volume governed more by spacetime's expansion than by local matter. Within such a void, even light itself could experience a tiny pull outward, altering round-trip communication delays and bending radio waves in ways never observed inside the heliosphere. Now, laboratory tests and cosmological simulations suggest that dark energy-dominated voids can produce minute phase shifts and amplitude modulations in traversing signals, effects that would show up on Voyager's instruments as coherent anomalies rather than just random noise. If Voyager 1 truly sampled a sliver of this cosmic foam, its data offer us the first direct in-situ glimpse of dark energy's influence on electromagnetic propagation. Confirming this pocket would not only rewrite our understanding of the interstellar medium, but also provide an unprecedented laboratory for testing whether fundamental constants remain unchanged in regions where dark energy reigns supreme. As Voyager 1 sails deeper into the void, every distorted waveform and delayed ping may map out the hidden architecture of the universe, and reveal how the silent force of dark energy sculpts the fabric of spacetime itself. Plasma filament interaction. Voyager 1's sensors just whispered of a hidden highway in the void, a dance with a ghostly plasma filament that left its instruments singing in synchrony. In the blink of an eye, the spacecraft crossed through a slender strand of interstellar plasma, an elongated ribbon of charged particles threaded by magnetic fields that acted like a cosmic waveguide. As Voyager tore through this filament, its detectors recorded a series of harmonized energy pulses and subtle magnetic fluctuations far more orderly than the usual cosmic roar. These narrowband emissions, first identified as a persistent hum in interstellar plasma, spanned multiple frequencies with consistent amplitude and spacing, signatures of a filament channeling and amplifying plasma oscillations rather than scattering them. Inside these filaments, density microstructures, ripples just a few thousand kilometers across, trace turbulent cascades in the interstellar medium, yet remain remarkably coherent over distances of billions of kilometers. As Voyager 1 pierced the filament, its plasma wave instrument saw sudden shifts in electron density and magnetic field strength that mirror laboratory studies of filamentary turbulence, where charged flows swirl around magnetic cores and generate organized oscillations. This encounter suggests that interstellar space is laced with invisible wires of plasma that can focus energy and guide electromagnetic waves, much like fiber optics over cosmic scales. Decoding the precise waveform patterns from this filamentary passage could reveal the filament's internal geometry, magnetic topology, and even the spectrum of turbulence within. By mapping these cosmic strands, Voyager 1 offers humanity its first in-situ glimpse of the interstellar web, a network of plasma filaments sculpting galaxies and guiding particles through the darkness between stars. Physics rewritten. Voyager 1 just dared the universe to redefine itself when its instruments logged a cascade of interlinked anomalies. Energy spikes, patterned pulses, phantom torque, accelerated echoes, silent sectors, alien-style beams, dark energy distortions, and plasma filaments, all in one astonishing episode. This isn't science fiction, it's a reality check for centuries-old physics. Traditional models treat interstellar space as a passive backdrop, a near-empty expanse where cosmic rays and magnetic fields drift predictably. Voyager 1's data totally shatters that illusion, revealing a dynamic, interactive medium capable of bending spacetime, guiding energy with dazzling precision, and even hosting phenomena that mimic intelligent design. If an advanced civilization's technology fine-tuned particle beams across light years, our theories of field propagation and energy dissipation will need a radical overhaul. If dark energy pockets truly warp electromagnetic signals in situ, we must rethink the scale invariance of fundamental forces and revisit cosmological constants. Should plasma filaments act like interstellar fiber optics, then turbulence theories and magneto-hydrodynamic simulations require major revisions. And if localized space-time warps shorten signal delays, we might finally glimpse pathways toward faster-than-light communication or travel, once banished to theoretical footnotes. Each hypothesis emerging from Voyager 1's impossible encounter demands new equations, fresh laboratory experiments, and innovative space missions. As scientists race to integrate these anomalies into coherent frameworks, textbooks will change, graduate programs will pivot, and the next generation of space probes could carry quantum sensors explicitly designed to map these exotic phenomena. Voyager 1, the humble messenger from humanity's past, has become the herald of physics' future, urging us to broaden our understanding of reality and embrace a cosmos that refuses to remain static or simple. Thanks for joining Simply Science on this incredible journey with Voyager 1's impossible encounter. If you enjoyed unraveling deep space mysteries, smash that subscribe button and ring the bell so you never miss our next cosmic discovery. Drop a comment below with your wildest theory about what Voyager might uncover next, and let's keep the conversation going. Your support helps us explore the universe one breakthrough at a time. See you in the next video, Space Explorers. In September of 2022, humanity officially became a cosmic force, capable of moving celestial objects through space. But what happened next, honestly, shocked even NASA's top scientists. When the DART spacecraft slammed into asteroid Dimorphos at 14,000 miles per hour, it didn't just nudge the space rock as planned. The impact created a 32-minute orbital change instead of the expected 10 minutes, proving our planetary defense technology is 3 times more powerful than we ever imagined. We didn't just deflect an asteroid, we revolutionized physics itself. The DART mission. What if I told you that on a Tuesday morning in September 2022, humanity officially became a space cowboy? That's exactly what happened when NASA's DART spacecraft smashed into asteroid Dimorphos at over 14,000 miles per hour, marking the first time our species deliberately changed the course of a celestial object. This wasn't just another space mission, this was our planetary defense debut. The double asteroid redirection test launched in November 2021 with one clear mission: prove we could knock an asteroid off course if one ever threatened Earth. Scientists chose Dimorphos, a football stadium-sized moon orbiting the larger asteroid Didymos, as the perfect target. Why? Because it was far enough away to be safe but close enough for telescopes to measure the results. The $325 million mission spent nearly a year traveling through space, guided by autonomous navigation systems that would steer the spacecraft into its target without human intervention. On September 26, 2022, at exactly 7:14 p.m. Eastern Daylight Time, DART completed its kamikaze mission, streaming live images back to Earth until the very moment of impact. Ground control erupted in cheers as confirmation arrived. Humanity had just taken its first real step toward becoming a spacefaring civilization capable of defending our home planet from cosmic threats. Impact Results Analysis. You know that moment when you throw a rock into a calm pond and watch the ripples spread? Well, multiply that by about 10 billion and you'll get close to what happened when DART hit Dimorphos. The moment of impact on September 26, 2022 created the most spectacular light show in our solar system, a massive debris plume that stretched over 10,000 kilometers into space, visible to telescopes across the globe. But here's the mind-blowing part. This wasn't just a little puff of dust. The impact crater ejected millions of tons of rock and debris at speeds reaching 500 meters per second, creating what scientists called a comet-like tail that persisted for months. Ground-based observatories and the Hubble Space Telescope captured breathtaking images, showing the asteroid system glowing like a distant star. The brightness increase was so dramatic that Dimorphos became 35 times brighter than normal, making it visible to amateur astronomers with basic equipment. What shocked researchers most was the duration of the debris cloud. Initial models predicted it would dissipate within days, but observations in November 2022 still showed active particle ejection. The European Southern Observatory tracked individual boulders the size of cars being hurled into space, while NASA's infrared telescopes detected the heat signature of the impact site glowing for weeks afterward. This spectacular aftermath proved that kinetic impact missions create far more dramatic and long-lasting effects than anyone had calculated. Momentum enhancement discovery. Scientists expected a gentle nudge. What they got was a cosmic sledgehammer effect that rewrote the laws of asteroid physics overnight. When NASA's mission planners originally calculated DART's impact, they predicted the collision would slow Dimorphos by exactly 10 minutes in its 11.9-hour orbit around Didymos. Conservative estimates based on laboratory simulations and computer models suggested this would be humanity's modest first step into planetary defense. But on October 11, 2022, when ground-based radar measurements finally confirmed the results, jaws dropped across the scientific community. The asteroid's orbital period had decreased by a staggering 32 minutes, more than triple the expected change. This wasn't just beating expectations, this was obliterating them. The momentum transfer efficiency reached 2.2 to 4.9 times higher than theoretical predictions, depending on which measurement method scientists used. Dr. Lori Glaze from NASA's Planetary Science Division called it a game-changing discovery that fundamentally altered our understanding of kinetic impactor technology. The reason? Dimorphos wasn't behaving like a solid rock, but more like a loose aggregate of boulders held together by weak gravity. When DART struck at 6.14 kilometers per second, it didn't just transfer its momentum, it triggered a massive recoil effect, as tons of debris shot out like a natural rocket thruster. This ejecta enhancement meant that future asteroid deflection missions could work with much smaller spacecraft than previously thought, revolutionizing our entire approach to planetary defense. Asteroid structure insights. Ever wondered what happens when you punch a pile of gravel versus a solid brick wall? That's exactly what DART's collision revealed about Dimorphos, and honestly, it completely shattered our assumptions about asteroid composition. Before September of 2022, scientists believed most asteroids were dense, rocky bodies that had formed billions of years ago during the early solar system. But when DART slammed into Dimorphos at 14,000 miles per hour, the impact didn't create the expected solid crater. Instead, it triggered what researchers called a catastrophic disruption that exposed the asteroid's true nature as a gravitationally bound rubble pile. High-resolution images from ground-based telescopes showed massive boulders, some the size of school buses, being ejected from the impact site, revealing that Dimorphos is essentially a loose collection of rocks held together by extremely weak gravitational forces. This discovery revolutionized our understanding of near-Earth objects, with Dr. Andy Rivkin from Johns Hopkins Applied Physics Laboratory confirming that 80% of asteroids in our cosmic neighborhood share this rubble pile structure. The implications are, well, staggering. These flying gravel heaps are much easier to deflect than solid asteroids, but they're also way more unpredictable in how they respond to impacts. Spectroscopic analysis conducted in late 2022 revealed that the ejected material contained primitive carbonaceous compounds dating back 4.6 billion years, making Dimorphos a time capsule from the solar system's violent birth. This insight means future deflection missions will need completely different strategies depending on whether they're targeting solid asteroids or these cosmic rubble piles. Strategic implications. What happens when humanity suddenly realizes it can literally move mountains in space? The moment DART's success was confirmed in October 2022, every space agency on Earth started rewriting their planetary defense playbooks. This wasn't just a scientific achievement, it was a species-level upgrade that transformed us from sitting ducks to active defenders of our cosmic neighborhood. The 32-minute orbital change proved that kinetic impactor technology could work with dramatically smaller spacecraft than previously calculated, meaning we could launch multiple deflection missions for the cost of one original estimate. NASA's Planetary Defense Coordination Office immediately began updating their threat assessment protocols, realizing that asteroids once considered too large to deflect were now manageable targets. But the implications go far beyond just Earth protection. International space treaties from the 1967 Outer Space Treaty suddenly needed modernization. Who has the authority to deflect an asteroid that might affect multiple countries? ESA's Director General Josef Aschbacher announced in early 2023 that the success had accelerated European Union space defense initiatives by at least 5 years. Meanwhile, China's National Space Administration and Russia's Roscosmos both fast-tracked their own asteroid deflection programs, creating a new space race focused on planetary protection rather than exploration. The most surprising strategic shift came from commercial space companies like SpaceX and Blue Origin, who began developing rapid response deflection systems that could be deployed within 18 months of asteroid detection, turning planetary defense from a decades-long project into something resembling an emergency response system. We officially entered the era where extinction-level threats became manageable engineering problems. Hera mission planning. What do you do when you've just pulled off humanity's greatest cosmic billiard shot and need to see the damage up close? You send in the forensic investigators. That's exactly what ESA's Hera mission represents, a $129 million space detective story launching in October 2024 to examine DART's crime scene with unprecedented detail. While DART was the muscle, Hera is the brains, equipped with advanced imaging systems and 2 CubeSat companions called Juventus and Milani that will map every crater, boulder, and debris trail left behind by the September 2022 impact. The mission will spend 2 years traveling to the Didymos system, arriving in late 2026 to conduct the most thorough asteroid autopsy in human history. Hera's instruments include high-resolution cameras, laser altimeters, and ground-penetrating radar that will create 3-dimensional maps showing exactly how Dimorphos deformed during impact. But here's where it gets fascinating. Juventus will actually land on Dimorphos and drill into its surface, analyzing the internal structure that made DART's momentum transfer so surprisingly effective. Meanwhile, Milani will study the dust environment and track particles still orbiting the asteroid system 4 years after impact. ESA's mission planners designed Hera to answer the biggest question: can we scale up this technology for real planetary threats? The data collected will feed directly into NASA's next-generation deflection systems, creating a complete blueprint for asteroid defense architecture. When Hera arrives at Didymos, it won't just be studying the past, it'll be engineering humanity's cosmic security system for the future. Planetary defense evolution. Remember when humanity's biggest space worry was whether satellites would crash into each other? Those days, honestly, officially ended when DART proved we could weaponize physics itself against cosmic threats. The September 2022 success didn't just validate one mission, it triggered a complete evolutionary leap in how our species approaches planetary defense. Within months of impact confirmation, space agencies worldwide began developing second-generation deflection technologies that frankly make DART look like a prototype. NASA's follow-up missions now include multiple kinetic impactors working in coordinated strikes, gravity tractors for precision orbit adjustments, and even nuclear pulse units for the most extreme scenarios. Japan's JAXA announced their 2028 Hayabusa X mission will test precision drilling techniques to alter asteroid rotation, while India's ISRO is developing swarm deflection technology using dozens of small spacecraft acting as a collective force. The most revolutionary change, though, came from private sector involvement. SpaceX began designing Falcon Heavy variants specifically for rapid asteroid response, cutting deployment time from years to months. ESA's 2025 Planetary Defense Conference established the International Asteroid Response Protocol, creating standardized procedures for global cooperation during real threats. But perhaps the biggest evolution is philosophical. We've shifted from reactive astronomy to proactive cosmic engineering. Ground-based surveys like NASA's NEO Surveyor and ESA's FlyEye telescopes now operate as early warning systems feeding directly into automated deflection networks. What started as humanity taking its first baby steps into planetary defense has evolved into a sophisticated cosmic immune system that actively monitors and neutralizes threats before they become extinction events. Mission success redefinition. When was the last time scientists had to completely rewrite what winning means in the middle of celebrating victory? Well, that's exactly what happened when DART's results came back showing a 32-minute orbital shift instead of the predicted 10 minutes. Suddenly, every planetary defense mission in development had to recalibrate their success metrics. Before October 2022, mission planners used these pretty conservative models based on solid asteroid physics and laboratory impact tests that assumed only modest momentum transfer rates. NASA's original benchmarks actually classified anything above 73 seconds of orbital change as a complete success, making DART's 32-minute achievement an almost 2,600% overperformance. This unexpected triumph forced JPL engineers to completely revise their deflection calculators and threat assessment algorithms. Dr. Tom Statler from NASA headquarters even admitted that success parameters for future missions like ESA's Hera and NASA's proposed NEO interceptor needed fundamental restructuring. The ripple effects were immediate asteroid deflection timelines that once required decades of advance warning could now work with just years of preparation. International space law committees had to redefine minimum deflection requirements for planetary protection protocols, while commercial space contractors realized they could bid for asteroid deflection contracts using much smaller, cheaper spacecraft. Most importantly, the scientific community learned that real-world asteroid physics operated on completely different principles than computer simulations suggested. Mission success was no longer about hitting predetermined targets. It was about adaptive engineering that could harness these unexpected physical phenomena. DART didn't just succeed, it redefined success itself, proving that sometimes the best victories are the ones that exceed every prediction and force humanity to dream bigger. Debris management and safety concerns. What happens when you create the largest artificial debris field in human history and suddenly realize it might come back to haunt you? That's the uncomfortable question NASA scientists faced when DART's impact on September 26, 2022 scattered millions of tons of asteroid fragments across space at velocities reaching 500 meters per second. While everyone celebrated the 32-minute orbital success, space debris experts quietly began tracking what they called the Dimorphos particle cloud, an expanding sphere of rocky projectiles that could pose risks to future spacecraft missions. ESA's Space Debris Office immediately activated enhanced tracking protocols using ground-based radar systems to monitor the largest fragments, some weighing several tons and traveling on unpredictable trajectories. The October 2022 debris analysis revealed that particles were spreading far beyond the Didymos system, with some fragments potentially reaching Earth-crossing orbits within decades. Commercial satellite operators like SpaceX and OneWeb began incorporating DART debris models into their collision avoidance systems, while NASA's Orbital Debris Program Office updated their space traffic management protocols to account for artificial asteroid fragmentation. The most concerning discovery came in early 2023 when optical telescopes detected boulder-sized chunks still being ejected from Dimorphos months after impact, suggesting the asteroid was experiencing ongoing structural collapse. International Space Station mission planners now include DART debris assessments in their orbital safety calculations, and future asteroid deflection missions must prove they won't create navigational hazards for deep space exploration. The irony is pretty striking. Humanity's first successful planetary defense created our first interplanetary pollution problem. Precision requirements for real threats. What good is humanity's newfound cosmic billiard skills if we can't hit the balls that actually matter? While DART's triumph against Dimorphos was spectacular, deflecting a real Earth-threatening asteroid requires precision levels that make Swiss watchmaking look like finger painting. The sobering reality hit scientists in early 2023 when they calculated the exact requirements for real planetary defense scenarios. Unlike Dimorphos, which was a harmless test target 11 million kilometers away, an actual extinction-level asteroid would need deflection decades before impact, and missing by even 0.01% could mean the difference between a near miss and global catastrophe. NASA's Planetary Defense Office revealed that successful deflection of a 1-kilometer asteroid discovered just 10 years before Earth impact would require trajectory accuracy within 10 meters at the moment of collision. Imagine threading a needle while blindfolded and riding a rocket. The challenge multiplies when dealing with fast-rotating asteroids or binary systems like Didymos, where gravitational interactions can amplify small errors into massive miscalculations. ESA's trajectory modeling in 2024 showed that deflecting Apophis during its 2029 close approach would demand navigation precision exceeding anything achieved in human spaceflight history. Perhaps most daunting, detection systems like NASA's NEOWISE and the upcoming NEO Surveyor must provide asteroid composition data, rotation periods, and structural characteristics years in advance because with real threats there are no second chances. DART proved we can move asteroids, but defending Earth means hitting cosmic bullseyes with zero margin for error. And that's how humanity officially became cosmic defenders in just one incredible impact. From DART's sledgehammer effect to the 32-minute orbital miracle, we've proven that extinction-level threats are now manageable engineering problems. But this is just the beginning of our planetary defense evolution. What amazed you most about DART's discoveries? Drop your thoughts in the comments below. I read every single one. If this blew your mind like it did mine, smash that subscribe button and hit the bell icon so you never miss Simply Science breaking down the universe's most incredible mysteries. Until next time, keep exploring.